Hi, welcome to the this today. So this will be a 1 hour session today. So this session I've requested NPTEL and they fortunately agreed to give the session to me. So it will be 1 hour session up to 8 p.m. Okay. So okay. So before starting further, let me know whether I'm audible and is the screen visible to you or not. Please let me know.
Yes, it is audible and visible too.
Okay, thank you, Mr. Confirmation. Okay, so before starting, so before we starting further, please let me know, do you have any question or any doubt from previous sessions?
No, no.
Okay, since there is no doubt, so let's start 1 minute. Okay, so okay, so since there is doubt, so let me give some questions by my own. Okay, so please try to solve it with yourself. Take your time. Okay, so it will be 1 hour session. So there were 3 or 4 questions which I have um, so there are 3 or 4 questions which I have thought to give. Okay, so let me write the questions. One minute. Okay, so the questions are as follows. First question is that so let y be Hausdorff space and f g from x to y be two maps. Okay, show that show that all those x belongs to x such that fx equal to gx is a closed set. See, such a thing, I hope such a thing you have already seen in where? Such a thing you have already seen in case of metric space. Of course, in case of real analysis, you have seen such a thing, right? But one minute. Huh. But in case of topology, such a thing is also true. But of course, for example, in matrix, you have proved this using um, some sequential character continuity functions. But in topology, we don't have general things like that. So try to figure out how you can approach this problem. Okay, it shouldn't be difficult. Take your time. Let me know. Basically, one extra thing that has been given is that y is Hausdorff. So try the only hint. Okay, so one hint I can give is that since y is Hausdorff, so its diagonal is closed in y cross y. Now use it. Try to use it basically. I mean, the point is that what I mean, the counter which I told you is basically the same thing. Okay, anyway, that's not a big deal. The big deal is that so try to show that delta is closed in y cross y. Okay, take your time. Let me know. So let me explain. Okay, just one. So is it working really fine? Okay. So the point is that, so this given set, this thing, we need to come up with this set, right? So define a function h, what to have x to y cross y. Okay, we're sending x going to fx comma gx. Okay, now clearly if we call the given set, then clearly x belongs to x such that fx equal to gx, this particular set equal to h inverse of delta y, right? Now delta of y is closed as y Hausdorff, and so this implies h inverse delta of y is also closed as h continuous. So this tells that our given set x belongs to fx equal to g, that is also a closed set. Okay, is that clear? Please let me know. Is that clear? Please let me know. Okay. Okay. So I hope this clear. So if not clear, please, Mustaki, if it's not clear to you anything, then please unmute yourself and ask a question. Okay, because these sessions are meant for problem solving. Okay, so please try to utilize this session as much as you can. Okay. Now the next question. The next question is that is Q is locally compact. So that is the question. So of course, Mustaq, we have done this particular question previously also, but I think these questions are interesting to recall that how we have solved this. Okay, because now we are at this end of the session and exam will knock in the door very soon. Okay, so show that Q is locally compact. So can you tell how to approach this problem? Any idea? Any guess? Take your time, let me know. Take your time, let me know. So let me re-explain. See, if I mean, of course, you know the answer is not locally compact. So I mean, so the point is, suppose it's a method by method of contradiction. The method of contradiction. Okay. If Q locally compact, if Q is locally compact, then if Q is locally compact, then what we what we can do is that, so we choose a point x, and that x will lie in a compact set which is inside some open set. Okay, now what we'll do, we'll choose a sequence Rn such that this sequence Rn goes to x. Okay, now x belongs to k, and the sequence Rn this also lies to k, but k is compact, and also assume that Rn goes to x. So this implies what? X belongs to irrationals, but such a thing is not possible. So let me explain. So we have assumed that Q is locally compact. Okay, that means the point x belongs to open AB intersection Q. Okay, and x belongs to k, so Rn subset of, Rn subset of k. Okay, now Rn goes to x, so x belongs to Q complement. So that is the argument. So there is nothing to explain more. Okay, so that is the argument. Okay, so the next question is as follows. Show that show that every compact metrizable space X has a countable basis, so that every compact metrizable X has a countable basis. Okay, so that is the thing you need to prove. Okay, so take your time, let me know. Musta, please try. So the argument goes as follows. Okay. So solution goes as follows. Okay. So first of all, so it's compact metrizable base. Okay. So we can start with some open cover of X. So it will has a finite subcover, right? Okay. Now, and the open covering is the open set of n balls of radius 1 by n. Okay, of course such a cover exists. Okay, so x equal union x, that is x belongs to union x belongs to x, b of x comma 1 by n, and it admits a finite subcover. Okay, the constant countable set beta is equal to union of a n, n belongs to n. Claim is that this beta is a basis for x. How to do that? So for that, what we need to choose x belongs to x and delta greater than 0. Okay, we wish to show that there exists some b belongs to b such that x belongs to b subset of b of x comma delta. What are we are fixing a n greater than 2 by delta. Okay, and letting beta belongs to a n which contains x, then x belongs to b subset of bx comma delta. And indeed this tells that for any y belongs to b, d of xy less than 2 by n, this is less than delta, so y belongs to b of x comma delta. Okay, so that is the argument. Is that clear, Mustaq? Mustaq, is that clear? Okay, I hope it is clear. So now let's go for the next problem. The next problem is that, okay, so there is a very interesting problem. So this problem show that every metrizable Lindelof counter basis, every metrizable Lindelof space has countable bases. Proof. So how to prove that? Okay, first think about it. I shall be back in a few moments. So, well, so how to approach this problem? So this problem can be approached as follows. Who's not able to figure this out? How to solve this? Please let me know. Okay. So just hold a moment, please. Okay. Okay. So it can be done as follows. See, so X metrizable space. So D is countable dense. Subset. Okay. Now putting beta is equal to B of x1 by n. N belongs to n, x belongs to t. And of course, it is easy to show, you can easy to show that beta is a countable basis. So this beta will work actually just in the previous problem. Just use same technique as previous problem. So it should not be difficult. Just hold, take your time and let me know. Okay. Okay. Now the next question. Show that. So this next question is okay. Show that if x has a countable basis beta n, then every basis c of x contains a countable basis for x. If x a countable basis beta n, then every basis c of x contains a countable basis for x. Okay. So try to show this. Take your time. Let me know. Okay. It shouldn't be difficult, I guess. So this problem is like the just previous one we have checked. So basically we need to replicate the method of the previous problems. So that is the thing. Okay, so yeah, take your time. Oh, so that is the argument. So okay, so that's okay. So that so okay, so there is nothing to explain. So please take your time. Let me know. Okay, so the argument goes as follows. So the argument goes as follows. Now the point is that where is okay. So the argument goes as follows. Okay, so for each mn, if possible, choose Cmn belongs to C such that Bn subset of Cnm subset of Bm. Okay, and oh shit, there is some issue with this whiteboard, I guess. Hold a moment, please. Okay. So we C belongs to such a Bn subset of Cm subset of Pm. Such a thing is always true. Okay. Now, we have that. Okay. Now we claim that this countable subset of C is a basis. Okay. For this, what we need to choose x belongs to x. Okay, and we need to find Bm, the basis element. One. Okay. So now we are taking Bm, a basis element that contains x. Okay. Now since C is a basis, so there exists some C belongs to C such that x belongs to C subset of Bm. Okay. Now since Bm is a basis, there exists n such that x belongs to Bn sub of C. Now as Bn subset of C subset of Bm, so this tells that Cmn such that x belongs to Cmn subset of Bm. So this is the way we are proving this. So basically what we're doing is that so basically what we are doing is that 1 minute. Okay, so basically what we're doing is that, so we're choosing a countable subset C as from the basis, and then what we're doing is that Bm is a basis that contains X. Now since C is a basis, so for the error exists C belongs to C, so X belongs to subset of C. Now since Bm is a basis, so the error exists N, so the X belongs to Bn subset. Now as Bn subset of C is subset of Bm, so we will have a CMN, so the X belongs to CMN, less subset of Bm. Okay, so that is the thing. So yeah, so that is the argument. So now there is the next question is that a G delta set in a space X is a set A that equals the countable intersection sorry, there is some issue each and every time it is. So that equals the countable intersection. Okay, countable intersection of open sets, countable intersection of what, of open sets of X. Okay, now show that in a first countable space every one point set is a G delta set. So that in every first countable space every 1 point set is a G delta set. Okay, so yeah. So yeah, so think about it and let me know. Hello, sir. So please take your time, think about it. Okay. So, mm, okay. So the argument goes as follows. See, first of all, see, first of all, the thing is, first of all, the thing is that, okay. So we're choosing x, a 1.76 x, and beta be a countable basis at x. Okay. Now we claim that u is equal to intersection b belongs to b singleton x, and so this will be singleton x. Okay. For that, what we're doing is that you are choosing. So choose y belongs to x with y not equal to x. Okay. Now since x is t1, so there exists an open set V such that x belongs to u does not belongs to y. Okay. And letting uh, beta be a basis element such that x belongs to b subset of u. So we see that y does not belongs to b. So therefore, y does not belongs to w, and w equal to singleton x. Okay. So that is the argument. So that is the argument. Okay. Now, one. Hmm. Now the next question is that, so this next question is that, show that if X is a countable product of spaces having countable dense offsets, then X has a countable dense offset. Then X has countable dense offset. Okay. Take your time, think about it. Let me know. Okay. So this argument goes as follows. See, since so xn are the spaces and an countable dense subset, so basically a natural case is that the product over an, this product will be countable dense sub of x. Okay, so how this product will be, countable dense. So countability is not an issue. We need to use denseness. So dense means closure of n. We need to take whole closure. I need to check this is the whole of x. So this is will be by the formula product of n closure, and each n is a countable dense. So that was what product for x, and that is x. So this tells that each product of n will be countable dense subset of x. So that is the argument. Okay, is that clear? I hope so. Okay, so okay, so that's all for today. We shall meet on next Friday, this time 7 to 9 p.m. 7 to 9, yes, 7 to 9 p.m. Yeah. So the fine, so we will meet on next Friday from 7 to 9, and that was the last session for this course. Okay, and then you have exam editor. So please do prepare properly. If you have any doubt or any issue, please do let me know via email. Okay. Okay. Thank you. I'm leaving the session.